All right. I think I'm unmuted now. Thumbs up. You can hear me. Okay. So hello, everyone. Again, my name is Monica Mattox, and I am the Oklahoma Assistant State Climatologist with the Oklahoma Climate Survey and the MESNet. And I was asked to talk to y'all about climate and fire. So just to jump into this, we're going to start with a little word association. So when I say the word fire, I want you to think about what comes to mind and just hold that thought there. Okay, so fire. What are you thinking? What's the first image that comes to mind? Okay, so here we have a couple different forms of fire. We have a bonfire under A, we have a house fire with B, a prescribed burn in C, and then a wildfire in D. So which of these images came to your mind from fire? And I want you to put the letter in the chat box so we can see what you guys were thinking. D, D, A, lots of D's. There's a C. Wow, this is kind of overwhelmingly C and D right now. Is everybody getting their word association in the chat? There's a B. I'm sorry, there's a B. So A and C are more positive uses and associations with fire. Recreation, time with family and friends, some prescribed burning to help with like ranching and land management. While B and D are more of the detrimental side of the impacts of fire. And this goes to show that fire means a lot of different things to a lot of people. It's meaningful to all of us in one way or another. And today, we're actually going to focus on wildfires in particular, with special emphasis on Oklahoma, Texas, and New Mexico, because I think that we have some folks from all of those areas. Okay, so here we're going to do that Kahoot game that Emma was talking about. So if everyone can go to kahoot.it, I used my phone before and it worked out really well. We're gonna do some trivia and see how knowledgeable you all are. Okay, and then when you're there, you should be getting a pin. And I want you to put the pin in. And then you can go ahead and put a code name in. It doesn't have to be real. It can be like, I always wanted this name from birth, if you want. Someone wanted to be called Yazzie, all right. So I'll give you guys a second. So once you're at this kahoot.it, put that pin in and then come up with a code name. And then we'll start. The pin is 9311752. And you should see that on my screen right now, hopefully. Okay, so we got quite a few of you folks in. So now we're gonna test this knowledge, all right? Okay, so I'm gonna give you a question and you're gonna select the best answer. All right, question one, between 2002 and 2019, which year did Oklahoma experience the highest number of fires? 2002, 08, 11, or 17? These answers are flying in right now. 3 seconds. Okay. All right. So a lot of you thought 2011. We have some winners with 2005. Look at that, Sean, you're winning already. Okay, the next question. So the last one was numbers of fires. Now we're gonna look at acres burned. Which year for most acres burned for Oklahoma? Same period. Okay, oh wow, okay, so a lot of you got that one right, that's awesome. Sean, did you take it away again? Donuts. Donuts is winning. Okay, the next question. Now this is for Texas. Same question as the first one, number of year for fires in Texas.
Hey, buddy.
Yes, Sean did help with this yesterday. Okay, so this one was a little bit tougher. Donuts is still on top. Okay, which year saw the most acres burned in Texas? Megan, it's okay, I wasn't there either. Okay, the correct answer was 2011. There's Yazzie taking a win. Okay, New Mexico, highest number of fires. I said we were going to focus on these 3 states in the beginning because we have some participants from there. Ooh, this was kind of split with most of you. So some of you thought 2006, some thought 2011. 2006 was the right answer. Michael Scott, I would love to meet Michael Scott. Okay, so he's winning right now. Number 6 for New Mexico. Wow, a lot of you got that one. 2011 had the most acres burned for New Mexico. Still winning, Michael Scott. And then our last question. 2 scientists walk into a bar. The third one ducks. I'll have H2O says the first. I'll have H2O2 says the second. The second one dies. Scientists won't go into a bar, it's a pandemic, and then and a table and chairs. I'm giving you a moment to think about this. Okay. 25 people in. Let's see who got this one right. 18 seconds left. Do we have anyone? Wow. Okay. I see how this is going. And I actually like that 9 of you got that joke for the H2O. Okay. Let's see. Bonanza third. E second. Michael Scott is first. All right. So what this means is actually that Michael Scott gets to take over hosting abilities for the rest of the talk. No, okay, we don't want to do that. Okay, I'm gonna close that. So now we're gonna do, we're gonna look at the graphs that kind of went into that quiz. And I want you to feel free to chime in, type in the chat box some of your thoughts with these graphs that I'm going to show. Okay, so this data is from the National Interagency Fire Center, and these were questions 1 and 2. So what do you notice? Again, type in chat, let me know what you think. Where are some peaks? Where are some trends? Where are you seeing less? What are your thoughts? And just type that in the chat box. Okay, less wildfires in recent years, but more devastating in acreage. Katie said that. Most fires were not during most extreme drought periods. Fires were more frequent by smaller area burned. Man, I don't even know if I have to give this talk. I feel like you guys are golden. Seems like nonlinear trend increasing and decreasing both. Okay, so we have some observations here. I want you guys to keep those in mind because now we're going to look at the next state. Here is Texas. What are your thoughts? Trends? Lack of trends? We have those winning answers that you can see in some of these graphs, like 2008 being the highest number, but 2011 having the most acres. 2 years peak with others. Someone said more correlated here. 2011 was a very bad year. Yep. Okay. And then New Mexico. These were questions 5 and 6. It's a little bit different than the other two. So what are you seeing with this? More consistent fires. Yeah, a lot more steady numbers. Less variance in the number of fires. Total number of annual fires is not correlated with annual acres burned. Okay, you guys are doing awesome. So I'm going to close the chat and we're going to move on to the next one. Okay, so let's look at some of these numbers compared by state. So I also want you to make sure that you are looking at the y-axis and you see that these are different for each graph. So based on these plots, we can see Texas seems to have a lot more fires. It's also a large state. And they're all pretty different. Oklahoma appeared to have more during the early part of this period. Texas seemed to have more later in the period. New Mexico is relatively low if you're looking at the y-axis compared to the others, but you're still getting decent fires consistently with New Mexico. Okay, and then here is acreage compared by state. Again, not seeing acreage burned or severity necessarily at the same time as those frequency peaks or at the same time as some of those other states. So more fires doesn't necessarily correlate with a lot of acreage burned per se. You could have fewer fires, but bigger ones. So for Oklahoma and Texas in particular, numbers didn't really match acreage burned, and this can explain a little bit why. So based on the science and the previous talks, we know that temperatures are going to rise, but we also have good indication that there are going to be more extreme events. So this is showing the top 3 megafires for each state, which is a fire that burns more than 100,000 acres. The East Amarillo complex was the second largest in the US, but not the most destructive, which I actually think was the Bastrop fire from 2011. According to reports, the 2006 fire in Texas was part of a really intense fire period, both for Oklahoma and Texas, for late 2005, early 2000s. And that was primarily because of prolonged drought and really strong winds. So that resulted in 25 deaths, 4 of which were firefighters, evacuation of thousands of people, hundreds of destroyed homes and structures, and a loss of 2,000 miles of fencing and 5,000 head of cattle. So then we have the Northwest Oklahoma complex, and that was the 4th largest in the US during this period. And what else is interesting is that some of these large fires occurred in recent years, and we're going to touch on that later. So the top right photo, it's a little bit grainy, but it is from the 2006 mega fire in Texas. And in that photo, a rancher is trying to save his ranch by disking the fire line, which I bet quite a few of you know like what that means. So they're creating a ground barrier using their tractor and kind of trying to prevent the fire from jumping the road and continuing on. The bottom photo is Oklahoma rancher Greg Gardner, and that is from 2017 when he's assessing the damage from that Northwest complex fire. He lost hundreds of cattle in that event, and you can see that in the photo. It's pretty sad. So these are the people, these are our friends, these are our colleagues who are getting impacted directly by wildfires. So scaling back from the state picture and looking at things nationally, this is showing area burned by large wildfires from 1984 to 2014. And we can see an increase in area with moderate to high severity. And burn severity is the amount of fire damage to the forest canopy. And then with severity increasing, there will be more impacts to tree regeneration, things like timber production, other ecosystem services, water quality, recreation, etc. So you know what else is impacted? The economy, dollars. So money that goes toward fire suppression. And that's what this graph is showing for the entire US. Inflation kind of aside, we still see this increasing trend with this graph. Other states like California have seen some serious fires recently, and that could kind of be playing a part in the trend that you're seeing here. But in general, the data and the trends like this should be getting us thinking about how humans play a role. So population, development, people living closer to that wildland-urban interface, that threshold where communities are more at risk of wildfire. And as natural resource managers, these are risks to consider. And we all know that allocation of resources are incredibly, incredibly important. So as more money is required, there could be competing resources, including financially. So needless to say, fire is a huge part of that human experience. And we see those impacts in the different ways that we just mentioned. And you all know this, right? So there are so many direct and indirect effects from fire. Some positive, so the prescribed burning, the seed regeneration, also some negative. Fire can impact the economy, habitats, our land, our health. It impacts recreation, access to resources, and cultural and indigenous traditions. And a lot of these are interrelated, right? So what if we have a fire that disrupts the ecosystem that then reduces water quality and impacts our health? I think that if you were going to put this in social media terms, you would say our relationship with fire is complicated. And so if we think about the way we relate to fire and how it impacts us, we also need to start thinking about what makes fire tick. And it can be summarized by this fire trifecta for these 3 primary factors. So an increase in population or human interaction with the environment, land use and fuels, and climate and weather conditions. An increase in human activity can increase the likelihood of ignition. Changing land use practices can result in a resurgence of native grasslands and fuel. And drought, seasonal variability, and fire-conducive weather systems can also increase the threat of fire. So first, just real briefly, I want to touch on the history and impact of human activity and land use change because it is an important player with fire and we need to consider it. So fire actually helped create the plains. It was used to modify habitats and aid in things like hunting in the past. Since the early 1900s, however, there has actually been a reduction in prescribed burning. This increased native vegetation growth and also increased the growth of invasive species like red cedar and mesquite. All of this really meant an increase in vegetative fuels available for burning, especially red cedars, which have large diameters and create really high intensity fires. And in this region, it's also more human activity and I guess increased infrastructure than necessarily population that can increase the ignition threat. So this can often come from train tracks, vehicles, power lines, etc. And in fact, the most common igniter is actually power lines. But with that in mind and in the spirit of natural resource management and climate change, we're going to focus primarily on the weather and climate ingredients moving forward. So let's look at some of the short-term meteorological fire ingredients. Okay, first off, precipitation, which I think kind of seems like a no-brainer in a way. It's tough to get fire in the moment when it's raining. But also, rainfall affects the soil moisture and the moisture of dead fuel. So wet fuel is harder to catch and doesn't act as really good kindling. Next is temperature. And warmer temperatures can increase evapotranspiration so that water from the soil and the plants evaporating and transferring to the atmosphere. And that can reduce relative humidity and fuel moisture, and that really can act as a feedback loop. This takes us to relative humidity, which is an incredibly significant factor. So relative humidity is the amount of water vapor in the air compared to how much the air can hold at that temperature. So it's kind of like the moisture in the air. The lower the relative humidity, basically the drier the environment, which impacts moisture content of fuels. And dry fuels means more to burn. Last but certainly not least, we have wind. So wind is so important. The speed and direction can drastically impact fire containment and spread, and it can drive the direction of flames and smoke. And I will show you an example of this in a real world scenario later. So here are some useful weather thresholds I just wanted to share. This is from the Oklahoma Mesnet's OK Fire program that indicate an increase in fire danger once these thresholds are passed. So relative humidity is seen as 1%, and when conditions are between 35 and 85% dropping, you know fire danger is increasing. Below 35%, containment becomes difficult with the risk of quick ignition and spot fires. 20% is kind of the extreme fire behavior threshold, and that's when spot fires become way more frequent. For wind speed, anything greater than 20 miles per hour is increasingly problematic. Higher speeds cause increased fire danger and spread rates. And then for temperature in general, really, the higher the temperatures, the higher the potential for fire danger. Long-term temperatures can also set a backdrop for fire conditions, which we'll be hitting on. So moving on to kind of the larger scale climatological drivers of fire, these are just some of the key ones that I'll be getting into. So seasonal fluctuations of wet dry periods, or dipole events as they're called, those are a significant factor. Alternating periods of drought and heavy rainfall events, that's what those are. Those working together can act as really good predictors for the fire season. So dipole events, like I said, are those alternating periods of significant drought and rainfall. And I want you to think about the wet-dry relationship a little bit like this. So you have a lot of rainfall, which creates vegetative growth and fuel loading. Then it gets dry. You shut off that fuel loading and you cook it. This kind of creates the perfect conditions and kindling for fire. The 4th National Climate Assessment states that periods of abundant precipitation followed by drought and high temperatures are linked to increased wildfire activity in our region. Okay, so let's look at how half that equation has been going for us. So here we have some figures showing how extreme precipitation events have been changing through time. On the left, the figure is comparing maximum daily precip in 5-year blocks through time with the 99th percentile events to the right of that, at the top of that figure. And then basically, we're looking at heavy precipitation events changing through time. So what this shows is that our region has been seeing an increase in heavy precipitation events. The graph on the right supports this by showing an increase in extreme 2-day rain events dating back to 1900. Now, you might think that this is a little counterintuitive, which it seems like it is, but large scale, this ties into that concept of alternating extreme events and dipole events. So we saw historic and current trends, but what if we look ahead at those climate change projections? What can we expect? So this should be familiar from the previous talks, but these are the precipitation projections with the high emission scenario out to 2099 relative to that 1976-2005 average. So the biggest takeaway is that we are in that striped area, which means that changes to average rainfall are likely relatively small. You are going to see some ups and downs depending where you are, when. However, I want you to keep in mind that it may not necessarily be about the average value, but more about in what form we are going to be receiving the rain. So sometimes averages have a tendency to kind of hide some of those extremes. And observed trends and projections indicate potential for an increase in extreme rain events or flooding with more dry periods and drought in between those events. So speaking of drought, drought is rainfall's secret partner in crime. It's also super friendly with La Nina. So La Nina is the cold phase of sea surface temperatures in the Pacific, which shifts the jet stream north. And this can lead to warm and dry conditions for the southern United States, which means that La Nina favors drought and thus fire conditions. So drought leads to dry soils and stressed vegetation, making vegetation more flammable. It's also been linked to higher potential for ignition, fire spread, and large fire events. So here's your brief PSA for the day. This is your pond, and this is your pond on drought. Say no to drought. Unfortunately, I think we've been trying. It doesn't really work. And please feel free to Google PSA videos from the 80s if I am officially too old where this does not make sense to anyone. Okay, so now let's look at nature's oven, both to grow to some extent and then to cook vegetation. So here are temperature observations compared to the first half of the last century. What we've seen, again, has not really been uniform, but we do see a good increase in winter temperatures and then some spots of cooling and warming in the summer months. And rising temperatures are causing changes to growing season length, fire season, all that we need to keep in mind, especially when we're thinking about available fuel. And here's that point again about averages hiding some of the extremes. So we not only see an increase in temperature averages, but we also see the occurrence of record-setting daily temperatures in the United States. So the red bars on the graph represent more daily record highs, and the blue bars are more record lows. So we're seeing an increase in daily record highs, extremes, and warm events. Those hot days, coupled with the other important factors that we're talking about, can really prime the environment for fire. So what do potential temperature averages and extremes look like in the future? So here are those National Climate Assessment temperature projections again. I think that it's safe to say we all know it's going to warm, right? But based on these maps, and for this region in particular, we're looking at an increase of 3.6 to 5.1 degrees Fahrenheit in the high emission scenario by mid-century. And then an increase of about 4.4 to 8.4 degrees by late century. Extreme-wise, here are the projected number of days above 100 degrees for the Southern Plains. We see an increase in roughly 20 days to as much as 50 days in the low scenario on the left. With the high emission scenario on the right, we see a pretty large increase. So ranging from an increase of about anywhere from 30 days to 80 or so days. And that's a lot. That's enough for me to want to move back to Michigan, frankly. But it's projected that extreme heat will become more common. Temperatures similar to the summer of 2011 will become increasingly likely to reoccur, particularly under these higher scenarios. So we looked at observations and precipitation and temperature projections, but here's the thing that we really need to consider. So how do all of these things work together? If you neglect the flour in the cake mix, the cake's not gonna bake right. If you forget the bacon in anything, you may as well just chuck the whole thing out, really. All of these things work together to prime our environment for fire. So let's recap real quick. So a significant factor are these dipole events with wet and then very dry periods. Extreme events are and will increase, and in particular, temperature, rainfall, and drought. Okay, so we talk a lot about individual weather and climate drivers, but what's also crucial is knowing how this is going to play out in the real world, including for decision makers and natural resource managers. So what does it look like to stack the dominoes and combine all of these variables? What happens when we put all of these things together? Specifically, what played out for March 6, 2017 in Northwest Oklahoma? So was it dry? On the left is the Drought Monitor map for the week of the event. And on the right is the departure from average rainfall in the Oklahoma Panhandle from January 1st, 2017 through the end of March that year. We were not in a La Nina, but looking at the image on the left, we did see some drought in the region. We had abnormally dry conditions all the way to severe drought in a lot of Oklahoma, with extreme drought in the Oklahoma Panhandle and then a tiny part of Southwest Kansas, which is the red shaded area in those maps. On the graph on the right, we see below average rainfall leading up to March 2017. It wasn't really until afterward that we started seeing some rainfall returning to the area. So looking at this, it's safe to say we were dry. We met those dry conditions. So zooming out a bit, did we also see a more long-term coupling of wet and dry periods? So the graph shows daily rainfall from Beaver, Oklahoma for the period January 2016 through March of 2017. And in this plot, there is a fairly wet period shown in the orange box during the summer and spring of 2016. After that, things kind of dry up and are really especially dry with little to no rainfall leading right up to March 6th. So this means there was plenty of opportunity to get vegetative growth and then build up of that fuel. So the evidence of this wet to dry variation could have absolutely aided in this being a fire event. So how were temperatures looking for this event? Were we warm? Absolutely. In fact, we were under a low-level thermal ridge, which played a major role in the fire threat this day. So a low-level thermal ridge is a region of warm temperatures near the surface that often experiences warm air moving in ahead of a cold front. Fire activity often occurs along these thermal ridges where there are warm temperature anomalies. And the bottom left image shows maximum temperatures for March 6th. The region we're looking at is kind of smack dab in the middle of a very evident thermal ridge, which is that inverted tongue looking thing in the map, with highs between 70 and 80 degrees. Just for a similar reference, the top right image shows a thermal ridge with warm temperature anomalies in red. And if you look really closely at that image in the top right, you can see black specks in the satellite image, and that is showing areas of fire underneath that thermal ridge. And that was from fires in April of 2009. Another major factor that day were the wind speeds. So there was a mid-level wind speed maxima in place, which really just means an area of highest wind speed overlapping that thermal ridge. And the image shows the wind maxima with the green arrows leading into that region of dashed red lines, which is the thermal ridge. So winds were around 110 knots, so 127 miles per hour, leading into the region just behind the thermal ridge. The mid-level wind maxima combined with the thermal ridge really helps create those ideal fire conditions. And it's where the two come together that you typically see the most significant fire activity. So like the image on the previous slide, if you look really closely at this one, you can see a bunch of black spots where the thermal ridge and the winds really align, and that's where those fires were. So what were the forecasters saying at the Storm Prediction Center leading up to this event? So we have a 1-week outlook in the bottom center that really is saying, hey, we need to keep an eye on this region for days 3 through 6. The left image shows the day 3 fire outlook, which kind of hones in on the area a little bit more. And it outlines the probability of strong winds, low relative humidity, and warm temperatures concurrent for at least 3 hours with dry fuels. By day 1, on the bottom right, extreme fire danger is outlined in purple from New Mexico and then kind of diagonally up through the Oklahoma and Texas panhandles and into Kansas. So really, the forecasters hit the nail on the head with this one. So ultimately, the ingredients came together perfectly, which caused the dominoes to fall for this event. So according to the Weather Forecast Office, fuel loading had been building over time, drought was impacting the area, and a dangerous combination of that thermal ridge and wind maxima were in place to create these fire conditions. It was, unfortunately, in a way, the perfect firestorm. So during the March 6th, 2017 Southern Great Plains Wildfire Outbreak, there were 32 major fires, nearly 1.3 million acres burned, 87 structures were destroyed, and then there were 7 fatalities and 5 injuries. It was the largest individual plains fire outbreak in modern history. And what made it very unique was the occurrence of multiple mega fires, both in Texas and Oklahoma, and we talked about that for a second in the beginning. So these high intensity fires are known for causing immense damage and extremely poor air quality. And they're very large, intense, uncontrollable, which makes them extremely dangerous fires. The left and center images show locations of fires during this outbreak with those dots. And then the Perryton fire is seen in the image on the right. So here's the GOES infrared image for you, and this shows the heat energy or fire temperature signatures from the outbreak on this day. And you can see the wind shifting from westerly, southwesterly to northerly. See, it's going, and then it drops. There's that shift. So this made the fires especially dangerous, as flank fires nearly 40 miles long became the new head fires as that wind shifted. So this is why monitoring weather at the time is also important when looking at the big picture of things. So not just to forecast, but to keep an eye on changing weather conditions that can impact what's happening on the ground. So this was a historic event. The dominoes were stacked and they really fell. So these factors, all of them, these components that we just talked about, will continue to play a part in future wildfire susceptibility. So this is what we can summarize about climate change from that 4th National Climate Assessment of the Southern Plains chapter, and after discussing projections and talking about extremes. So climate change is projected to increase average temperatures, increase frequency, duration, and intensity of extreme heat events, and a reduction in extreme cold events, increase drought duration and severity, cause small changes to average annual precip in the region with slightly wetter winters and drier summers, as well as an increase in frequency and intensity of heavy precipitation, which implies fewer soaking rains and more time to dry out between events, with an increase in soil moisture stress. And then also less future soil moisture, with future conditions possibly drier than anything experienced by the region during at least the past 1,000 years, according to that climate assessment. So what does this mean for the future of wildfires? So increased frequency and size of large, severe forest fires are expected in the United States. In the Western US, this is exacerbated by increased temps, earlier spring snowmelt, and a longer fire season. In the Southern Plains, wildfire risk will increase throughout the region as temperatures rise, particularly in the summer, and as the duration of the fire season increases. But also note that forest fire extent, frequency, and intensity will still also depend strongly on local ecosystem properties, which are going to vary across the country. So as decision makers and resource managers, it's important to recognize and know what to look out for when it comes to the primary fire ingredients. Consider how land management may play a role in fuel load. Know how conditions are projected to change so that you can plan for the future. And we can just think about, Emma's opening slides. Instead of looking at the rear view mirror, we need to start looking ahead. And of course, continue to grow awareness for you, for others, educate, and be a perpetual student, which you guys are already doing so much just by participating in this workshop alone. And that's all I have for you. We got this, okay? We'll take this information, we'll learn from it, and we'll prepare.